Okay, if you can Google it, that's great. You got to be able to name it to Google it. So I guess I can't be mad about that.
I'm not. No, I'm using
You're using the table.
the table
Okay. Good. Oh man,
on Google.
my table on Google. Oh.
Pull up the table.
I doubt my table is on Google, but who knows? Can I get some discussion from you guys? What ones do you feel the most confident on? And which are you not even sure how to analyze?
Yes.
Right.
Yeah,
Good.
I agree.
So none of them stand out to you as particularly easy to rank based on the pKa table?
Negative charges make things less acidic.
Ah, okay. This is actually a good point. pKa tables often show just a conjugate acid and its pKa, although sometimes it's conjugate base as well. And the pKa table that I've given you has conjugate acid and conjugate base. The way that I think about pKa's, and I think the way that most chemists think about pKa's, is a forward backwards. If you are looking at the acid, a more positive pKa means worse acid. But if you're looking at the conjugate base, which doesn't always even have a reported pKa, a more positive pKa of its conjugate acid means you're looking at a more powerful base. So you use pKa on these to think about how basic they are, considering the conjugate acid they form with that pKa. So I'm saying rank by pKa, and what I'm actually saying is rank by the pKa of their conjugate acid. So we're using pKa. These should technically have pKb because they're bases. We're using pKa to rank their basicity. Does that make sense? So on your table, you should not be looking at conjugate acids on the left. And I'm telling them to use the table that's on the home page of our Canvas course. You shouldn't be using the side on the left, which is the conjugate acids, but you should identify something that looks more like the compound on the right, the conjugate base. Did that help you? Because you're right, James, that a more negative compound is less acidic, but these all have the same amount of negative charge. So I can't say, oh, this that's 2 minus is more basic, or this that's 1 plus is the least basic. They all have the same amount of charge. Maybe you're not convinced about that because there's no charge written here, there's no charge written here, there's no charge written here, there's a charge written here. But Li, I know we show it as a covalent bond, but I told you to also think of it as being ionic. This is ionic, Na bonded to a carbon atom, and this, although we are showing it as covalent, does behave ionic. So, also, Christina, I love what you've done. You've taken in-butene and you've translated it into its structure to give you a better picture of what you're looking at. That's what I wanted you to do. That's why I gave you the abbreviation in-butene, so that you could think about transforming it into the structure. Okay, can we categorize these groups at all? What do you think? Do you see anything on your table that looks familiar to anything you see here? How about this? When we talk about acidity, we can often use cario to rank things. C stands for charge. A stands for atom. And that's misleading because actually you want to compare atoms that are in the same row by their electronegativity and atoms that are in the same column by their polarizability. So atom actually has 2 different designators. Okay, R, resonance. I, induction. O, okay. Is the charge different on any of these? It does kind of look like it, but technically these are all basically ionic bonds, and this one has a negative charge explicitly. So no, they actually all have a negative charge on the carbon. Is the atom different? The basic atom that we're looking at. It's all carbon, right? This is the base. This is the base. Lithium is not a base. Lithium doesn't own those electrons. That's why it's C minus. You can think of in Bewley as basically being this ionic compound. Carbon has a lone pair again, so that's the carbon is the base. And then here, again, we can kind of think of this as an ionic complex. So the atom is the same. Is there any resonance distinction between these compounds? A is fully conjugated. In fact, we have a better descriptor for A, right? A is what type of compound? A is an aromatic compound. So where is that negative charge? Where is that lone pair? Delocalized. It's across the whole ring, which means each carbon is technically like a minus fifth charge. So resonance in this one, how do you think that might impact acidity? Increases acidity. Oh, I'm sorry. So how does that change the pKa? Lowers it. So because of this aromaticity, this probably has a lower pKa than you would otherwise expect. But we still don't know really how to rank it against these other ones. Induction. Is there any difference in induction between these groups? Not really. Like, there's no heteroatoms. There are sometimes, like, more carbon chains around, and carbon chains kind of act like electron donating groups. They have an inductive effect in rather than an inductive pulling effect, an inductive pushing effect. But honestly, I would say no, they're all pretty close to each other in terms of induction. There's, again, no heteroatoms to change that. I do want to say one more thing about resonance real quick. Some might look at this lone pair and say, could I push this lone pair in and push it out onto another carbon? But you really can't, because resonance is the movement of pi electrons in p orbitals, and this lone pair is sitting in what type of orbital? sp. This is an sp carbon. It has one of its sp orbitals making a sigma bond, two of its p orbitals making the pi bonds. The only other orbital left is the other sp. This is an sp2 carbon. Where is the lone pair sitting here? Is it in an sp2 orbital, or is it in a p orbital? sp2. This sp2 carbon has sp2 sigma, sp2 sigma, sp2 lone pair, and p in the pi bond. So this is, neither of these are capable of resonance because their electrons are not in p orbitals. Their electrons are in hybridized orbitals. Can't do resonance even if you want to try and do some silly electron pushing. All right. Orbital. How do the orbitals differ here? Correct. This has the most S character, middle S character, least S character, no S character. So I guess that one kind of falls out of the system, right? Because that lone pair is in what type of orbital? It has to be in a p orbital if it's fully conjugated. If it's a delocalized lone pair, it's in a p orbital. And how does S character change acidity? More S character, more acidic. More S character, a weaker base. So what do you think? What is the compound with the lowest pKa? You know what? I'm gonna say the least basic, and that is to say it has the most negative pKa. I say most negative, even though none of these actually have a negative pKa, because it's hard to say bigger or smaller pKa when it spans positive and negatives, and I don't want to say higher or lower. So more negative pKa. Which of these is the least basic, and which of these is the most basic? That is, it has the conjugate acid with the highest pKa. I think it's easiest to say which of these has the highest pKa. Yeah. Because we said based on orbital, which is really the only difference between these three groups. Based on orbital, the more S character you have, SP, the less basic you are. The less S character you have, the less acidic you are. So this is actually the most, the least acidic, the most basic. And this is actually the confusing part because P really does have the least amount of S character, but this has truly more resonance than the others. And you can even kind of argue the least charge because which carbon you look at only has a negative fifth charge. That's less negative charge, that's less basic. All right, then what would you say? D, the sp2 carbon. This was the sp3 carbon, the sp2 carbon. All right, now we're really down to it. How can we compare the sp hybridized carbon and the aromatic carbon? What would you guess has the lower pKa? Think about resonance. You should. That resonance is going to have a very big impact on the acidity. So then we're looking at C here, SP, and we're looking at A as the least basic, aromatic. Aromatic being the reason why. Should you be drawing a line in between the alkyne and the sodium, or no, because it's not? I do not see it as a covalent bond. I see it as an ionic bond. But again, your textbook will say, look, it's the first time you saw an organometallic was all the way back when we made this. It's like, okay, well, this is another organometallic then, if you're going to be so bold. This is calcium carbide, and that C2 has this structure. So calcium carbide is an organometallic. Most people would say calcium carbide is a mineral, more so than an organometallic, because it's crystalline and it's hard and it's still basic. That's true, but I don't know if I've ever heard somebody describe it as an organometallic. And sorry, I wanted to show this, but I don't know why it didn't log me in.
Has he done any reactions yet?
Nope, this is it. Okay. So remember, using this pKa table on our homepage, we can see down here the sp3 hybridized carbon. That's got a pKa in the 50s to 60s. Then the sp2 hybridized carbon in the 40s. Then, actually skip a few, the sp hybridized carbon in the 20s. The one that actually resembles our aromatic the most is this, the one that's ranked carbonyl. The alpha carbon of the carbonyl has that resonance with an oxygen. To be fair, this aromatic compound does not have resonance with an oxygen, but it has resonance with 4 carbons. So there's some like balancing effect, right? It has a similar pKa to the 15 to 20. All right, why do I bring up ranking the pKa of these compounds that we had worked to synthesize in our last class? Because today we're going to start with reactions with organometallics. One thing that we can do with organometallics is run substitution. We have just generated strong nucleophiles and also strong bases. Now, because these are such strong bases, we need to be careful about what type of alkyl halide we run them on. If we go for a tertiary alkyl halide, straight to elimination. These would love to take a hydrogen, and so they will run elimination instead. But on a less substituted carbon, we can run SN2. So let's see if you can predict the product from this reaction. Phenolithium plus isobutyl bromide.
What are you ranking on the left?
pKa, like it says at the top, and on the sides,
Ranking pKa.
the carbons.
The will commonly seen in this unit.
It's going to be, we'll talk about pKa's in this unit, so this is a good conversation about acid-base character. Here's a reminder about how to draw these types of products. I like to count through the nucleophilic attack to make sure I don't lose any of my atoms. And I say atoms, not just carbons, because you can count through oxygen atoms, count through nitrogen atoms, whatever you need. Here's my nucleophile. So I'm actually going to start back here and count 1, 2. This is my nucleophilic carbon. Oh, no, it's not. Guys, I'm sorry. That is the electrophilic carbon. What's my nucleophilic carbon? The organometallic carbon. I apologize. That's my nucleophile. And here is my electrophile. So if I count through the nucleophilic attack, it is the aromatic carbon attacking the primary carbon, which is connected to this tertiary carbon and then this primary carbon. So I'm going to map out this 4-carbon chain to predict my product. Carbon 1 attacks carbon 2, connected to 3, connected to 4. True. Byproduct here, LIBR. Again, we want to avoid secondary and tertiary alkyl halides. You can try, but if you ran something like tert-butyl chloride with N-butyl, you'll just run elimination, E2. And actually the cool byproduct here is that you get N-butyl, or excuse me, N-butyl, N-butane. and the lithium chloride.
Why did that just run you through?
High steric strength at the electrophilic carbon. So as your nucleophile tries to come in to substitute, it has this huge energy barrier to go over. And you know what has a much lower energy barrier? Grabbing a hydrogen. Because it wants to grab a hydrogen anyways. So it runs over a different area energy barrier. It goes through elimination. Remember that these are magnets. So you're just pushing these magnets close together and you're seeing how they attract each other and change bonds. It would take a lot of energy to get it to do substitution, and it takes very little energy to do the elimination in comparison. Another side point to this. We should probably, I'm not going to say only because I don't want you to feel like it's not out of the picture. But we should prefer Gilman reagents when using aryl halides. Those are the halogens bonded to an aromatic ring. Remember the Gilman reagent, the other term for it? R2CuRi is a terrible name though, because it's just a lot of letters. Yeah, lithium diorganocuprates, or the diorganocuprates, or the organocuprates, or the cuprates.
How does that end with an R2 cubic?
Cuprate is what I like because it's just easier, but so if we take this in the reverse, remember that we can abbreviate the diorganocuprate instead of having to draw the organo portion twice. We can use these parentheses and say subscript 2. But you have to show the parentheses or you're not drawing the actual structure. So if we flip this on its head, we can still get the same product. But this time the nucleophilic carbon actually changes. Here the nucleophilic carbon is carbon 3 and it attacks carbon 4 as I've numbered it, because again, I like to count through the nucleophilic attack. Can you tell me the byproducts?
Carbon takes a +2, or copper takes a +2, right?
No, this is actually copper 1. This is not copper 2. Copper plus, not copper 2 plus.
Okay. You just get
Copper plus 1. So 2 bonds is negative, so it wouldn't be bromine.
Why is lithium there?
you get bromine gas.
You don't get bromine gas. No, just one equivalence.
Half of it.
Yeah, lithium balances the charge, which is to say copper is neutral if it's only bonded to one of those groups.
Is it still LIBR and elemental copper?
Not elemental copper. LIBR is one of them. How many of the alkyl groups did we actually use? One of the 2. So the other byproduct is the R group bonded to copper. That's neutral.
Is this preferred because it's an easier reaction?
So the reason it's preferred, this has a transition. It's actually not a transition state. This has an intermediate. Where copper uses its d orbitals to do things that lithium and magnesium cannot do. Lithium copper dissects the aryl halide. Eats it up. Yum, yum, yum.
Lithium's just floating around.
Lithium is still balancing the charge. This still has a net negative charge.
Oh, it's on.
And so lithium is still there balancing the charge. But you can see how the aryl halide bond has been broken. And actually, this is how the carbon-carbon bond can be formed. Copper will keep 2 of the electrons, and the other 2 electrons will go with the halogen, the 2 carbons, and they'll push off this new product. There's names to all of these things. They're doing some pretty fun stuff. That's inorganic chemistry. We're not going to dive into it too heavily here. In fact, this is part of the mechanism, and I'm not asking you to show the mechanism for this. You guys are fine with that? Okay. I would say that you can definitely propose a reaction similar to this. Let's just abbreviate it here and show methyl Grignard. You could absolutely propose this. I wouldn't even take off points for it because it is a seemingly very valid proposal. And we can rationalize the intermediate. What type of reaction is that? It is substitution. Is it SN1, SN2, or SNAR?
SN1.
It's not SN1. It actually has two. It has 2 reagents in the rate determining step, which means that it's second order nucleophilic. So it's technically SN2, but SN2 is a very specific mechanism. It's a backside attack. And this is not a backside attack, correct? Yeah. This is addition followed by elimination, as all aromatic substitutions are. Addition followed by elimination. So this is SNAR. Not SN1, not SN2. The reason it's not SN1 requires the C-Br bond breaking and creating a carbocation that the nucleophile bonds to. That's not stable on sp2 carbons. SN2 requires a backside attack. That would mean attacking from within the ring. That's impossible as well. So the only way this can happen is by SNAR. What are the reagents that we showed doing SNAR back in that chapter? NAS. Give me something. OH minus, OR minus, NH2 minus, NR2 minus, NHR minus. We saw hydroxide, alkoxides, and amides, not the functional group, but the anion. Is carbon here a stronger nucleophile than those, or a weaker nucleophile than those? What did you say? No. Carbon is a stronger nucleophile. What do nucleophiles do with their electrons? They share them. Who shares better, carbon or oxygen? Carbon. So remember, within a row, you can actually rank nucleophilicity by electronegativity. The less electronegative, the stronger the nucleophile. And then actually in a family, the larger the polarizability, the larger the nucleophile. So sulfur, less electronegative than oxygen, but a better nucleophile. Anyways, SNAR. So what I'm trying to say is there are people out there that would like to say, try to use a Gilman if you're going to do substitution on an aromatic ring. But I do feel like it's plausible to show substitution on an aromatic ring with this. Again, the textbooks are not always clear about what you should and should not do. So we're gonna. Does this make sense? Is it too vague? Am I stepping on my words? Doesn't make sense, does it? Okay. So we can do substitution. Great.
You didn't show us any Grignard reactions yet, right?
Congratulations. Here you go.
That was last week's slide. Yeah.
And this right here, this is, I mean, it's an organolithium, but organolithiums are basically the same family as Grignards, so this could have been a Grignard, and you could do it. Additionally, this could have been a cuprate, and you could do it. Cuprates will run this as well.
That's like how we made triphenylmethanol, right?
Yes and no. It wasn't substitution. It was this next reaction.
What are the nucleophile and electrophile? Is that so you can just add any two reagents? So there's 4 reagents to get you that product. What's attacking?
The nucleophile attacks.
What's the nucleophile?
I don't think I understand your question. What is the
No,
nucleophile?
he's labeling that carbon as the. He's labeling that carbon as the.
Oh,
The carbon with the negative charge is the nucleophilic carbon because it has a negative charge on it.
That's what the X was. The
Okay.
label.
All right. The second type of reaction we can run here, and we're not actually going to spend a lot of time on it because we're gonna cover it in more depth in a little bit, is acyl addition. The Gilman reagent can't do this though, and the Gilman is the cuprate. So I'm just going to show you generically what happens here. This is some carbonyl with 2 R groups. Right now, it is valid for us to say that they could both be carbon chains. One could be a hydrogen. They could both be hydrogens. There are some restrictions on what they can't be, but we'll get to that in a minute. And I've marked my organometallic as R prime to distinguish that carbon group. What this looks like is a ketone transforming into a tertiary alcohol. And we're going to come back to acyl addition later today, so I'm not going to spend too much time fleshing out the possibilities here. I just want you to recognize acyl addition. What is an acyl group? Carbonyl. And what is addition?
Removal of a pi bond.
Consuming a pi bond, removing a pi bond, opening a pi bond, yeah? And look at what has happened to the carbonyl bond. It's been added across. I added R prime and MgBr. But who the heck wants OMgBr or OLI if I was using an organolithium? No one. So if you were doing this in lab, you would follow this up with an aqueous workup. This is sometimes written as H3O+, sometimes written as H, sometimes written literally as aqueous workup. And now you can see we actually get the alcohol. Without the workup, you're left with just an ionic compound intermediate, an alkoxide.
So that oxygen is ionically bonded, right?
Yeah.
So acidic conditions just basically get rid of that oxygen's negative charge.
Protonate the oxygen.
Yeah.
Yep.
And so,
Oxygen acts as a base to
So
protonate.
do ionic bonds affect its ability to be protonated at all? I didn't think so. It's like a magnet, right?
Does the ionic bond change its ability to act as a base?
I'm kind of asking, does something being ionically bonded affect its ability to form covalent bonds?
I mean, yes and no. It depends maybe on your solvent. Yeah, because if you've got a solvent that is like really hindering that compound from, like you said, kind of being a magnet and going out and finding a proton, that might make it harder. But no, that ionic bond is not going to hinder protonation, really. Okay, any reason we would need to write this as 2 steps individually? We could summarize this and write it as carbonyl with Grignard. I'm actually going to substitute Grignard now for organolithium because I want you guys to recognize they're interchangeable. But I'm actually going to say first organometallic, second H3O+. I'm just going to write those 2 steps over each other so that I don't have to go through the process of writing out the intermediate. There are times we actually may want to capitalize on the ionic intermediate. Do something else with that O- besides just turning it into an alcohol. But if we don't want to, if we want to make an alcohol, just put it over the same arrow. Sound good? And then the other thing that we can do is conjugate addition.
So do you make it acidic before you add the Grignard?
What?
Is that
Add the Grignard, get the product, add the acid.
Okay.
Just like you did in lab. You added the Grignard, you got this intermediate, you added the acid. The next week, conjugate addition, only Gilman reagents. So it's kind of a trade-off. What type of addition reaction you want to do. Now we can differentiate between our 2 families. Here's what conjugate addition looks like. We call it conjugate addition because I have a conjugated carbonyl. I have the CO pi bond in an uninterrupted series with a carbon-carbon pi bond. This is a conjugated system. And to skip over the nuance here, first step, second step, we'll just show the acid workup straight away. And this is the cool part about conjugate addition. I preserve my carbonyl. I add across the conjugate. I add across the conjugated component. We're going to come back to this in Unit 5. So this is more like a teaser for you than anything. An idea that says Gilman and the organolithiums and the organomagnesium halides are not the same. They both do addition reactions in the context of carbonyls, but they actually run different addition reactions. Again, we're coming back to this later, but I could have given you this kind of clarifying example where this is also a conjugated carbonyl, just to prove that organolithiums and Grignards don't do conjugate addition. They will go straight for the carbonyl to do acyl addition. We'll talk more in Unit 5 about why that is. Does that sound good? Everybody good with this side on the substitution? All right.
Those 2 circles?
I'm saying that I've broken apart the benzene-bromine bond, and I'm going to form the carbon-carbon bond. Copper, having its d orbitals, can do some really cool inorganic chemistry with organic compounds.
Will we ever see, like, organo like sodium, lithium, ever?
Well, no, not really. But that's what some textbooks try to say, is that this is an organometallic.
And that's what you're saying, like, no, it's not. It's like zero.
Yeah, and like I don't want you to think of it in the same realm because it is a bit different than the Grignards and the organolithiums.
Even though they're in the same group.
Even though they're in the same family. And sodium and magnesium are in the same row. There's some distinction. There is a reagent, if you look back through my old materials, you're going to find this reagent called grubs. We're not going to talk about grubs, but I do want you to just have this awareness. Grubs reagent is another transition metal catalyst that can do olefin metathesis, where you take two alkenes and you swap the groups that are on them. So if you're going through this, if you're going through my old material, you may see questions that look like this, where we put grubs over the top. And I'll swap out these two groups on the outside for these two groups on the inside. 1, 2, 3, 4. I don't really like making 4-membered rings. It's just not very stable. So here's 5. So this makes this 5-membered ring where carbons 1 and 5 bond to each other. Carbons 6 and 7 are pushed out as ethylene gas, bubbles out of the reaction. That's very cool. Very useful in organic synthesis. Ring closing reaction. That's great. We can do ring closing reactions with our other organometallics as well, though. In fact, one of the ring closing reactions you've got is here. I'm going to have you guys work through this in a little bit. Here's the other thing that I want to talk about right now. Number 4. This is just general acid-base reactions. So I'm going to clarify a few issues with using our organometallics. Benzoic acid reacts with methyl lithium. This should make you think of acyl addition, because I have an acyl group. So I'm going to put first methyl lithium, and I'm going to follow this with an aqueous workup in the hopes that I get an alcohol, right? Similar to how our acyl addition worked over there. But the product I actually get is benzoic acid plus methane plus some lithium hydroxide byproduct. What? I didn't do acyl addition, right? What did I do? I protonated the carbon. My carbon acted as a base. Why would it act as a base? Because it's incredibly basic, and I'm in the presence of a very strong acid. Nucleophile, base, electrophile, acid. This is a carboxylate group where, because of resonance, that negative charge is delocalized across both carbons. Both oxygens. So I can't run organometallic reagents in the presence of a carboxylic acid. You just can't. They just do acid-base chemistry. So let's say this is one example. Let's look at another one. Let's say that I want to take this compound, (5-bromo 1-pentanol), and I want to do substitution with it. This time I'm going to use phenyl cuprate, diphenyl cuprate, because earlier I showed you that you can do substitution with the organolithium. I didn't highlight explicitly that you can do it with cuprates as well, and you can. And here I showed that you can run acid-base chemistry with organolithiums and Grignards. So I want to show you that you can also accidentally run acid-base chemistry with cuprates. Instead of getting any sort of substitution at the halogen, pH feels really weird to just write on its own, so I'm going to spell it out a little bit more. That strong nucleophile, that strong base, rather, simply deprotonates the alcohol, turns it into an alkoxide. So we have to be very careful about when and how we use organometallics. We cannot use organometallics in the presence of carboxylic acids. We cannot use organometallics in the presence of alcohols, or we just ruin the reaction. Does that sound fair? No?
Sure.
Okay. So, with these reactions in mind, here's what I want you to do. I want you to take ethyl cyclopentane and turn it into 1,1-diethyl cyclopentane. I want you to take 6-bromo 1-hexene. I want you to turn it into methoxycyclohexane. And I want you to take 1-phenylacetylene. And I want you to turn it into this bicyclic structure. Here are some tips. Count your carbons. Brainstorm what reactions might all need to be here, and work forward and backwards. There may be more than one correct way to do this, but they will all involve organometallics. I would like them to all involve organometallic chemistry. Why don't you guys pair up for this, or get in groups of 3? If you feel like you don't have much to contribute, that's okay. Give your classmates an opportunity to teach, because they will learn by teaching you. Let's spend about 10 minutes trying to go through these, so feel free to just pick your own pace. Start with the one you think you might have the easiest time solving. The front seat. Yep. Multi-step synthesis with organometallics.
How do you do that? You gotta get a carbocation here.
Carbocation with organometallics? Or in case it's not clear, you can use any additional reagents as necessary. So you've got a starting material, and then use any organic or inorganic reagents necessary to get you to the final product. You don't need to like only use specific things. Just add something that you think is going to be useful. It is not on Canvas. Sorry. I'll add it right now.
So that's why I'm like,
We'll just go with the most substituted one. Reaction. Oh, yeah, that is a good idea. Radical halogenation.
Okay, it is now on Canvas, and it is underneath the alcohols and phenols, like homework assignments.
thank you.
Yep. No, we haven't learned LAH yet. LAH is coming today.
For that group.
Oh, sorry. I thought you were saying LAH, which is lithium aluminum hydride. This is just acid-base equilibrium, right? This is a strong base, but this is also a weak acid, so you don't have very good equilibrium.
So just add a,
Can you make an organometallic on
what
the
is this? Propane with, no,
Oh, this is not one step, by the way. You guys know that? Multi-step.
ethane with a
So we're adding
lithium?
the organometallic in.
Yeah, lithium.
Well, I mean, there's, like I said, there's more than one way to do it.
Yeah.
But considering what you need to accomplish in that, there's really only one best way to do it.
How do you add lithium to lithium?
You need an alkyl halide, and then you add 2 equivalences of Li, and it becomes an organolithium.
So did you got the first one? We gotta use it all.
Okay. Yes. That's only 2 steps, though. Like, okay. I like the idea that you're saying, but you are doing substitution on a tertiary carbon. Earlier, I gave this example. Did I erase it?
Is it?
An ex-
oh,
No.
yeah, it's only on a prime.
So you wanna do substitution to a primary alkyl halide. You don't want to substitute a tertiary alkyl halide.
We gotta do the bromine another way.
So you placed a bromine on the tertiary carbon, and you want to do chemistry with that carbon, right? You want to make a carbon-carbon bond there.
Yeah.
But you can't substitute there as the electrophile, but you could attack from there as the nucleophile. Just have to turn it into a nucleophile. How could you turn that tertiary alkyl halide into a nucleophile? That's one way.
What do you say?
I can't tell you. It's cheating.
Does HBr work with that?
HBr and the starting material does nothing.
I didn't think so.
There's really only one thing you can do with alkanes. Just one thing. Burn them. Oh, 2 things. You can burn them and something more useful. No. Not really. It is a substitution, but it's not nucleophilic.
Oh, radical halogenation?
BR2 and FeBr3 is EAS. You need an aromatic ring. But radical halogenation would work. What are the reagents for that?
BR2 and white.
Right. Excellent. I like that you counted the carbons. You tried mapping them out, yeah? So you're seeing that there's 6 carbons here, and then there's
What do we need to do? We need to break it?
Two. Because I think got one. Oh, 1, 2, all the way to 6.
Oh, so we just do we just put a grignard in? The grignard like breaks it,
Not a
and then-
starting material, right?
and then
So
we
one question
add
we
it,
have to ask
and then we
is,
grubs it.
Is this carbon really this carbon? Is this carbon one?
You said
This
don't worry
carbon
about
one?
grubs, that's just something.
Or is
to
it
show
possible that
materials if you're using
this
this
carbon
setting.
But don't we need that for
this
this?
is carbon 6?
Oh, I'm not thinking about that.
Well, if we need it for
That's what
this,
you
then
said
why
when
not
you
need it
put-
for this?
You
That's
get
what you
this
said
good
when you
idea
put grubs on
where we want to
Yeah.
take the 6 carbons that are in the starting
I'm not
material
thinking about this.
and we want to connect
How
them
can you
to
put
each
it? How can you make a ring back together if you break it?
So that means on one end, I want to
Sorcery?
have
I
a
don't
nuclear
know.
file.
I really don't know.
On the other end,
Oh,
I want
it
to
won't.
have an electric file. And I want the
Because
nucleophile
it'll
on
just
one end of
like
the
take
molecule
it, scoot it
to
out.
attack the electrophile.
Oh yeah, no, no, no.
Well, if you do
Track
a
what I'm
close,
saying?
yeah. So you do a deal close or something like that. If you're gonna use it to
Oh
close.
yeah.
But
He didn't teach us a grignard one yet.
There's a lot of things we can do with an alkene. H2 hydrogenation, H3O plus hydration.
Oh, that's right.
We could do.
We can
there's a
just do
lot of
that.
BR2 halogenation, HBr hydrogenation. A lot of things we can do, but actually I want you to keep this group in mind in the product. What reaction?
No way, that's one intermediate.
That actually
Yeah,
gives
do you think we could do the top left one? Put a magnesium in there, take it out, or fit a magnesium in there, then substitute it. out.
Big review of all the reactions.
I don't know if this is how we.
Or you could Google it, grab your phone and say, alkene reaction that produces an ether. And try
See
to
if it
find
marks me down.
a reaction that
Mark
would
me
give
down.
you an ether group. Because that might tell us how to use the alkene. Did you track with what I'm saying?
I guess if I would.
No, it's okay. You're working on the top one.
That's okay. That one. That's the score. That's what I'm doing.
Sorry, just so I'm up to speed, so what you're saying is, we can turn one of the ends of the cell alkene into a Bunsen group and they're in this case, right?
We will need to get an ether into this molecule somehow,
Oh, okay,
so that there's an ether in the product.
and then it would be done through the alkene.
no, but it's not.
It's not aromatic.
Yeah.
Does it have to be on the opposite ends of the?
Well, we also want one of these carbons to attack the other carbon so that I can make a ring.
Oh, okay.
So your,
That's what we call a
We could just use
mechanism.
that.
and then we do the two
So,
lithium thing, and then
I need-
trade that.
This could
Wait,
turn
no,
into
I'm
an ether.
overcomplicating.
Basically.
I was
But
gonna
it's also
do
an
3 steps with 2 work, but
and I need
yeah. this,
to get something over there
uh,
that could also be a
Adding this
nucleophile or an electrophile,
SN2.
and so that they can react with each other. And while I'm
Thing
at
with
it,
lithium, I think.
why don't I see if there's a way I can get an ether?
Adding 2 more
Oh,
carbons.
okay.
Yeah.
Is there a specific reagent that causes them to close up, or is it just like if you have the electrophile on one end and the electrophile on the other end?
They'll attack each other.
Oh, okay.
Because more than likely, one of them will turn into a nucleophile before the other. And at that point, they, like a shoelace, they're very easy to find each other and they react very quickly.
Oh, okay. And so then the key would just be trying to get.
Mildly okay.
Okay.
So I have one main way of you guys getting to this, but there are technically more ways. You might want to review your old reactions. You might want to Google things to see how they can come up. A lot of ways to go through it.
To add the.
So is that what is that what
Oh, yeah.
Yeah. Yes.
What's the bio? Is there HBr back there?
No, I like the art.
I mean, but that's the this, right?
Oh, like that would
Oh, there's a
happen.
second one going up. So we have two LIBR.
Oh, this.
I mean,
this
probably-
This also produces Earlier we said, and I erased it sadly, but earlier we said that substitution does
So what can we do?
give us an ally X.
This is wrong because it's not aromatic.
Basically,
No, this is wrong
you can't
because you were
add
trying to do
this.
substitution
So basically,
with a tertiary alkyl halide. That will just give you elimination. Instead, I want this carbon to be the nucleophile on a primary carbon. You got 5 bonds.
Give these electrons back to carbon.
I do.
Yep, you do.
We
Yeah. Are stuck? Okay. Move on to the next one. If you've brainstormed as much as you can,
Right, you just make it.
see what the next one looks like. If that one seems weird, glance at the third one.
So there's no benefit in making it lithium
Why not? Making it the nucleophile?
because the lithium can only be done on the.
I have to change it or it disappears. Is it pretty though?
The picture.
I have to rotate my resource for them to
Mm.
notice it. You know what I mean?
Yeah.
I have to have it there to notice it, and then I
It just
become
becomes.
satiated to it.
Yeah,
and don't.
exactly. That's really cool.
This is cool.
Okay, sorry.
I don't have to put that on.
Right, so you've got an idea where you've got a
no, I'm
nucleophile and
thinking
an electrophile,
actually you took it
but you've got a tertiary electrophile and a very strong base. Which means this is just going to run elimination. But what if you swapped and you made this the nucleophile and this the electrophile?
So this part was fine.
Oh no, actually it's not. FeBr3 works on aromatic rings. This is not radical. This step you're trying to do is radical halogenation, but you're showing EAS, aromatic substitution.
Don't do that. Got it.
And Christina, I'll accept NVS, but I learned over the summer that NVS is really only effective at benzylic positions. I know it. I know. BR2 works great. There you go.
But
You see the difference between BR2 with light
What one are you on?
and BR2 with an iron catalyst? Light
You're on the
is
second
gonna
or third?
split bromine into two radicals. It's going to be radicals. The iron catalyst grabs the bromine.
Would you like to do the
And that allows for them to dissociate. Break apart.
Okay, so
No
now
radical.
I need to. Oh, you
So-
said make this.
Make this the nucleophile.
on
So turn that into an organic metallic.
maybe not the synthesis of the
Okay.
on the third
Have
one
of those
because it's an aromatic
That's
ring.
okay. It's okay.
If you can get an ortho director on it, then you can try and put a
Oh, you know what? I just.
try and put some group there. Just I'm guessing like an ethyl, and you just smack them together.
The ether at the
No,
same
I
time.
have.
But there's other ways to do it where you add the ether later. My vision was for you to add the
You just heat them
ether
up.
while you
Or
set it
do
up
an elimination.
for the rings to attack, the carbons to attack each other. This is nice. It's all just like a little notebook of all your reactions. I think we
Because I
covered.
can't keep anything straight.
I know. Yeah, I get it. Any brainstorming?
So if you got an ethyl here, could you heat it up and would it form that?
That would be too many carbons. 1, 2, 3.
Oh, here's
1, 2,
What about this
3.
one?
So ethyl would be too many carbons.
Oh,
But if you got
Methyl.
methyl there, no, I don't think it would work. Or magnesium.
what if about an
I think we can
alkene methyl?
methylene.
Methylene. Would that work?
No.
Kill some? No. I don't know.
Because that basically turns our. Alright, now I see your thought there. I'll turn this carbon 1 into an ether. So that I get some ether here. A couple of things. Na, NeOH. NaOH would be like sodium methoxide. That would be an ionic compound.
Where
And
do we show
NeOH
rings forming together?
Maybe it means when.
But if you have,
this.
if you're doing this, hydroboration oxidation, this is an alcohol at
I don't
first.
think we've.
If you want to turn that into a methyl ether, you actually use the alcohol
We've done enough without making carbon
substitution.
bonds
Yeah,
together.
1
You
degree.
want
Just have to
something
set
like
up the right
methyl
circumstances.
bromide, and the oxygen of the alcohol substitutes the bromine of methyl bromide and makes a methyl ether.
Oh, okay.
But this reaction doesn't actually set us up to create a nucleophile anywhere. So it's a good idea. It gets the ether group, but it doesn't allow us to bond the ring. Should we go through them?
Yeah.
Thank you guys for working hard on them. Number one,
It's hardly working.
ethyl cyclopentane to 1,1 diethyl cyclopentane. I erased it because it's been out there for a long time. And it was just acid-base chemistry. It was literally me telling you, avoid these things because they don't actually do what you want them to do. All right. Here's what I saw a lot of you doing, by the way. You took this first step to do radical halogenation at the most substituted position. This is really the only thing you can do with an alkane. Like Killian said, you could burn it as well. That's just not useful. So radical halogenation gives us the most substituted alkyl halide. Then, what a lot of you were trying to do, and I'm going to show this in red because it's not a good solution, is you were trying to take ethyl Grignard to run substitution. The problem is that you would get these two structural isomers out of this reaction. Because you have a tertiary alkyl halide and an aggressively strong base, you cannot do SN2 on tertiary carbons. It will just run E2. That's not ideal, not what we want. So what I'm trying to encourage you guys to do instead is, you want to substitute at that carbon. Why not make it the nucleophile instead of the electrophile? So let's add magnesium or 2 equivalences of Li.
There's just charge balancing at that point, right?
Yeah, it's just the nature of it. If you want to work with lithium, use 2 equivalences of Li. If you want to work with magnesium, which doesn't blow up in contact with the air, work with magnesium. Yeah. Now I have a nucleophile, and all I need left is an electrophile that still gives me that 2-carbon group. So here, if I call this carbon 1, my nucleophile, in the product, I want carbon 1 to bond to carbon 2, 2 to 3. So I need a reagent that has carbons 2 and 3 with a leaving group on carbon 2. Make that bromine, make that chlorine, make that iodine, make it a tosylate, a pseudohalide. There you go.
And get magnesium metal?
No, you'd get magnesium bromide in this because of just because of the reagents I've used.
Or magnesium dibromide?
Oh, Killian, come visit my Gen Chem class. Ionic compounds don't have prefixes because ionic compounds are named based on their balanced ionic charges. Magnesium is 2+, bromide is 1-. Everyone assumes, based on the nomenclature, magnesium bromide is MgBr2. That is its name. Okay?
Any halogen.
Could have been magnesium chloride. If this had been Cl, then this process would have given you magnesium bromide chloride. So here's the deal. A lot of you got very close to the idea. You had the electrophile, you had the nucleophile, but you forgot the caveat. You cannot have a tertiary electrophile. So flip it. Make that the nucleophile. Killian, I'm going to erase this. Do you need a picture of it?
I don't think I've ever shared a picture really big on the board.
I know. Oh, I have so many pictures in my phone I've never seen again after taking them. What questions do you guys have on that first synthesis? Do you see the route now? You see how to get there? No, this is not acyl addition. All right, in this synthesis,
Where did we?
one thing that I tell you guys to do with your reactions is count your carbons, map your carbons, brainstorm, work forward and backwards. There's a lot of ways to go here, though. In terms of brainstorming, though, I need to get one of those carbons on the end to attack one of the other carbon on the end. I need to take this 6-carbon chain, and I need to have some sort of intramolecular ring closing where one carbon attacks the other, and all 6 of them are a ring. Which one should attack which? I don't know. And which of those carbons in the chain is the carbon in the ring with the ether? Also, I don't know. Well, I know. I'm going to try to convince you guys how to know too. Okay, there are a lot of ways that we can use an alkene. Is there a way that we can use an alkene that generates an ether? Zinc option? There's one reaction that we learned with alkenes that gives us an ether product. Halo ether addition. All right, well, I'm going to brainstorm for a little bit without the halo group. If I could get a structure that looks like this, and here's carbons 1, 2, 3, 4, 5, 6, 1,6-dibromohexane. And then if I could turn one of them into an organometallic, it could attack the other carbon by substitution, and it would give me cyclohexane. So I want a bromine on the end, a bromine on the end, and I'll turn one of them into an organometallic. That can then attack the other one. So if I want to have an ether in here as well, there's actually a couple of ways I could do this. I could take the alkene and just do anti-Markovnikov HBr, HBr with H2O2. I could get cyclohexane. I could do radical halogenation to put a bromine here, and then I could do substitution to get an ether. That's a lot of steps. So instead, what I'm going to do is actually, I'm going to take advantage of this spot on my alkene to try and turn that into the ether carbon. So I'm going to add Br2 in methanol. I'm choosing methanol because that's the OR group that I want to get at the end. I want to have OCH3. This reaction is regio-specific. It's also stereo-specific. This is regio-specific. By the way, I'm going to map my carbons so that you can keep track of what I'm looking at here. Halogenation in the presence of an alcohol. Halo ether addition. Where does my halogen add? Carbon 1 or carbon 2? Good. Because the solvent, whether that's the alcohol or whether that's water, will always attack at the more substituted position. So I get Br here, and I get OCH3 here.
Does it attack first?
Sorry?
Does it attack first?
The ether, or the solvent?
Mm-hmm.
No, you form the bromonium ring,
Oh, yeah.
and then the bromonium ring is attacked and opened by the solvent. This last part is actually just going to happen in one step. I'm going to add 2 Li. Once again, I could be adding here just Mg. Those are totally equivalent. As soon as I make one of these carbons into the nucleophile, it's going to become this. I add lithium here, one of the carbons becomes the nucleophile. As the nucleophile, that carbon takes its electrons, attacks the electrophilic carbon, creates a carbon-carbon bond. Did you notice that's what we did here too? We created a carbon-carbon bond. And here, we're creating a carbon-carbon bond. Organometallics are best at making carbon-carbon bonds. That's what they do. This is generated, but as soon as this is generated, you can't isolate it. It attacks itself, and it makes that ring. And so here I've got 1, 2, 3, 4, 5, 6. And it was this carbon 1 to carbon 6 bond that I made in that last step. That one was a little bit more abstract. It was out there. I actually wanted to recall your halohydrin addition, or your haloether addition reaction. That's why I put that in there. Okay.
So, how is it that the electrons from atom 1 can reach all the way 6 or 5 atoms over to...
Have you ever seen a guy that took a rope and swung it up in the air and created a knot, or like a lasso, in the air? That's how. This is not a stiff spaghetti noodle. This is a wobbly spaghetti noodle. So it can wrap around and find itself. This is a strong magnet and a strong magnet, a negative and a positive. So that spaghetti noodle folds in on itself, snaps together. My example at the beginning of the semester, my window tie, it's literally that.
So what if you had just hexane,
Okay.
and you had a positive carbocation, anion? Sure. Cation, carbocation, and the
Yeah.
anion. Would they form together?
Yeah, good luck creating that. You're not gonna have those two things at the same time.
Because they would neutralize each other?
Because they can't both exist at the same time. That would just be incredibly challenging to make. The conditions that support a carbocation are not the same conditions that support a carbanion. So you won't get a carbanion and a carbocation on a hexane chain. That's about as close as you can get, actually. All right, here's the last one. There is something you need to pay attention to in this reaction. And that is, we add a carbon during this reaction. I've got my 6 carbons in the ring. I've got my 2 carbons of the alkene. I should have started counting this in a little bit of a different place. We add a carbon during this process. I was actually a little bit foolish when I made this because I had a vision for how you would use the organometallics that we just talked about. And then today when I handed it out, I was like, oh, you could get that other carbon in a much easier way. So there's a few ways to go about this. Do you guys have any suggestions, brainstorm ideas about what you could do here?
Do you run HBr on it to at least get an electron or
If you ran HBr, your bromine would add here. I want to make a bond between 4 and 5. So I would want Br on carbon 4.
HBr with H2O.
Yep, that would work. Or since we've used Br a lot, I'm going to use HCl with H2O2.
I'm going to choose HI at this point.
You could. Ain't no one going to stop you. Anti-Markovnikov HX addition using that peroxide. Now I've got a strong nucleophile, which means that I can add a 1-carbon electrophile.
NaNH2.
A 1-carbon electrophile. NaNH2 has no carbon and is a base. I want CH3.
OH.
No, OH
That would be.
in the presence of an organometallic, or I'm sorry, I haven't made that an organometallic yet.
You just run acid-base chemistry.
I don't have a nucleophile.
So now you have to add.
Sorry.
Mg.
Mg to make it an organometallic. I'm just jumping ahead of myself thinking I've got the organometallic already. MgCl. I add a 1 carbon electrophile, methyl iodide, methyl bromide, methyl chloride, methyl tosylate. And I end up increasing my carbon chain. Now I've got position 5. Okay, but there is one more important thing, and that is I need to do alkylation on the ring, right? I need to alkylate the aromatic ring. In order to do alkylation, I need to have an alkyl halide. So I'm going to run Br2 with light, which will allow me to do allylic halogenation.
And then does the bromine attack one of the hydrogens in the corner of the
No,
ring?
no,
No.
you should review your mechanism for alkylation.
Okay, I will.
Bromine, it will attack the iron 3 bromide catalyst that I'm about to add, and then it will come off and form a carbocation, and then that carbocation will be attacked by the ring. You guys are familiar with seeing alkylation using alkyl chloride, but we can use alkyl bromide here. I'm just going to add FeBr3 because I have my alkyl halide. I just need my catalyst, and I can do alkylation on the ring. FeBr3 is acting in the same way that AlCl3 acts as my catalyst. I did not expect you guys to have an easy time solving these. In fact, I intentionally did this so that we could go through these brainstorming problems together, so that we could look at mapping your carbons out a little bit more, so that we could look at tying all of these together. I'm never going to give you a unit test or exam problem that is 5 steps long. Although I might give you one like this, 3 steps. That is what I want you to be able to do. 2 steps, sure, but this one is a little bit vague. I don't think this one has a lot of direction in it. All right, I want you guys to take a quick break, but we actually have some more things to talk about coming in. So get up, move around, take 5 minutes, and we'll come back in here at 2:33 to pick up again. You do need to review your Oken 1 reactions. Actually, we're going to spend some time on that in a little bit. Yes, sir.
On the radical most stable on the most substituted carbon, or allylic, or benzoic.
Yep, in that order. So it goes here. And you actually are right that this is one of the possible structural isomers. There is another structural isomer here that looks like this. So if we produce both of them,
That's off. Is it on the phenol? You added another carbon.
no, I don't think I did. Here's the ring, 2, 3, 4. Here's the ring, 2, 3, 4.
Huh?
Do you agree now?
You moved the.
I erased the ring. That's the only thing I changed.
You moved it over. You moved the pi bond over.
Yes, Killian, I'm telling you that there are 2 products that form here. I
How'd you
call
move-
these 1,3 allylic.
How'd you move the
isomers.
pi bond over?
Okay.
How long has that been able to-
At this step, there is an intermediate that forms.
Is that the kinetic product? Oh, that's all.
Yes, kinetic product, thermodynamic.
I have switched them.
This is the intermediate that forms. But it doesn't look like that. I just taught Lewis dot structures to my Gen Chem class. And I told them, Lewis dot structures is like trying to explain how a molecule looks to a 5th grader, to a 5-year-old. Like, oh, the atoms bond together. It's not how an atom looks. It's not how a molecule looks. This is what it looks like, Killian.
Both exist at the same time.
Neither exists.
All of them.
There is a molecular orbital with a p-looking orbital on this carbon and this carbon that the radical is in. One electron with a region that looks like this. And my Gen Chem students, when I taught them about what orbitals look like, they were like, oh, so the electron can't go from like top to bottom because there's a node there. And electrons are only found in the lobes. Electrons are not found where there are nodes. And they said, so it can't go from top to bottom. And similarly, they would say something like, it can't go from side to side. No. It is there without going through the middle. And actually, I would say the same thing in a pool. If you have a wave that's going up and a wave that's coming down, technically, there is no wave right here in the middle. It's not higher, it's not lower. So how is it that the wave is on the left and the right without being in the middle? It's a wave. That's what waves do.
So you can choose. So in order for it to stabilize, then you would randomly choose one of them.
It will react from one of those two positions.
It's a 50-50.
It's not really 50-50. Kind of depends on your temperature. If you ran this at lower temperatures, you'll get the kinetic product. Because the two resonance forms aren't technically equal. You can try to visualize that by saying one of the lobes is bigger than the other. So the electron is in both places, but not all of the time.
But is that
Or not an equal amount of time.
It's because the ring.
Yes, the ring is helping to stabilize it here, so you actually see it there more of the time.
Oh, so we usually won't get that.
No, if you ran it at low temperatures, you'd get this. But if you run it at higher temperatures, you have a better chance of getting this. This is a more stable product. This has a more stable intermediate. This has a more stable
Is that?
radical, but a less stable alkene. This has a more stable alkene, but it's a less stable radical. I know that's confusing.
Oh, that's reaction 8.
Is next week PCC and Jones?
I guess it will be next week. Yeah.
Your favorite?
PCC and chromic acid.
I think you mean Jones.
It's hard to say, really. Who's Jones?
You don't know?
What's his first name?
You didn't look him up?
Jones.
Wow, you know him so well.
I'll look him up.
Mm-hmm. Yeah. You're gonna find out he's 3 guys in a trench coat. It's like Jone and S. Really. All right. We're moving on now from organometallics, and we're moving into alcohols and phenols.
We're in unit 4?
No, we're in unit 3.
Okay. It was
Could you imagine if I went to unit 4 without giving you your unit 3 test yet? Crazy. One thing I want to explore, again, because we talked about this earlier, is pKa's. I'm actually going to say pKa of OH groups. I'm not going to say ROH because I want to clarify something with you guys. So let's look at this compound, cyclohexanol. Let's look at this compound, phenol. And let's look at this compound, benzoic acid. Notice that the most acidic bond, the most acidic hydrogen, is the OH bond in all of these molecules. Do you know the approximate pKa range for an alcohol like cyclohexanol? 15 is good. Water, I think, has a pKa of 15.6, 15.8. This typically has a pKa that ranges from 15 to 18, depending on the nature of the alcohol. By the way, you know pKa is a logarithmic scale, so that's a range of like 1,000. 10 to 16, or 15 to 16 is times 10, 16 to 17 is 100, 15 to 18 is 1,000. So there are some alcohols that are 1,000 times more acidic than another alcohol. The pKa of a phenol is about 10. That's 10,000 times more acidic than a regular alcohol. For every one molecule of alcohol that acts as an acid, there are 10,000 molecules of phenol that act as an acid. And then we get the carboxylic acid. Do you know the pKa of this? It's lower than 15. Even though it actually has less resonance than phenol. It's, sorry, I did say lower than 15, but I meant lower than 5. These are typically about, I didn't mean 5, lower than 10. They're typically about 5. pKa of 15, pKa of 10, pKa of 5. Why is the pKa of phenol so much lower than that of regular alcohols? Resonance. Increased resonance. I'm not going to show all of the resonance forms, but I'll show you how the ring conjugates with that oxygen to delocalize its negative charge. And then there are 2 more, where 2 other carbons in the ring hold the negative charge. And then there's benzoic acid. Why is this so much lower than phenol? Yeah, that's why. It just lives up to its name. Does it have more resonance than phenol? To be fair, I did show the same number of resonance forms, but I'm skipping 2 of them. It has less resonance than phenol. So why is it more acidic?
Is it because of there's more atom, like the oxygens on it?
Yep. Here, atom has a stronger effect in just 2 resonance forms than these 4. I placed the negative charge on 2 oxygen atoms rather than placing the negative charge on 3 carbons. This is the weird thing about resonance and using karyo, is they don't always work collectively the way you'd expect. A lot of times, you can have increased resonance, but actually a smaller number of resonance with a better atom plays a bigger role. All right, now here's another compound. I want you guys to tell me what range you think the pKa falls in. Does it fall between, does it fall above alcohol, between alcohol and phenol, between phenol and carboxylic acid, below carboxylic acid, or is it pretty much at one of those ranges? In between.
Carboxylic acid and phenol.
So more acidic than a phenol, but still not as acidic as carboxylic acid. Yeah? What do you think is changing the pKa relative to just the phenol?
The positive charge on nitrogen.
The positive charge on nitrogen.
The nitro group.
All right. I don't think it's the positive charge on the nitrogen.
Is it
Or
being
something with the nitro.
electron withdrawing?
It's the fact that it's an electron withdrawing group. So here's my conjugate base, and I'm drawing out the nitro group now. We know that the phenol already conjugates to the ring. So we know that the conjugate base can already share its electrons into the ring. So if there is an electron withdrawing group, and if its position is orthopara, that's a big part. Oxygen makes a double bond, carbon-carbon double bond shifts over, carbon-carbon double bond moves out to be a carbon-nitrogen double bond, and then the NO double bond breaks open. So now I have an additional resonance form. I still have the 3 resonance forms where the carbons in the ring hold the charge. But I've got this additional resonance form where the nitro group holds the charge. So here's a good tip. Electron withdrawing groups give more negative pKa's due to induction. Any electron withdrawing group, regardless of its placement, has a positive effect on acidity. It strengthens acidity because it pulls electrons away, as electron withdrawing groups do. And by pulling electrons away, you make something a better acid because the conjugate base has its electrons more stabilized. However, orthopara positioned electron withdrawing groups give even more negative pKa due to the induction and the increased resonance form. A meta-placed electron withdrawing group does not contribute to resonance. It contributes to induction, but an orthopara electron withdrawing group contributes to induction and resonance. So we said this falls between the phenol and the carboxylic acid. But if this is this is para nitrophenol, how would meta nitrophenol compare?
Between 10 and 15?
Let's say, is it between phenol and para nitrophenol? Or is it between para nitrophenol and benzoic acid? This is less acidic than para. You know what? I don't know if I'm doing this right. Less acidic than orthonitrophenol. Sorry, para-nitrophenol. Okay? Electron withdrawing groups always have this effect. But if they're orthopara positioned, they have an even stronger effect. Man, we did such a good job doing our synthesis earlier. We're just running out a lot of time to do these. Here's what I want to do to wrap up our time. I want to cover the old reactions. The reactions that we have already seen to make alcohols. So I have given you this flow chart. If you'd like to copy this into your notes, great. If you'd like to organize this a different way, great. But I essentially just want to take us through the 6 different ways that we've already said we can form alcohols. So this is how I like to format this in your notes. I want this to be called synthesis of alcohols. And I always like to look at the reactions we've seen previously. Typically, I run through this as a list. But I think it just makes more sense to consolidate these into one image. By the way, I haven't uploaded this yet, our Unit 3 learning objectives, but I was spending some time before class putting these together. And I'm listing all of the reactions that I want you to know. This is similar to what we did before. So you don't have to guess. But was that one that John liked and he just didn't want to talk about? It's on here. It's something you should know. So the first one we ever looked at, halohydrin addition. Our reagents here are Br2 and H2O. This is regio-specific. The alcohol adds on the more substituted carbon. Acid-catalyzed hydration, H3O plus and H2O. What type of intermediate does this reaction have? A carbocation intermediate, and we know that because there's structural rearrangement. There was a hydrogen on this tertiary carbon. There is no longer a hydrogen on that tertiary carbon. I must have rearranged my structure. Reaction number 3, another hydration, oxymerc reduction. I am abbreviating it from oxymercuration reduction. This is a 2-step reaction. First, mercury acetate in water. Second, a reducing agent, sodium borohydride. The usefulness of this hydration reaction, the usefulness is that it's still Markovnikov without a carbocation intermediate. I suppose you guys want to go home, huh? Why don't we end it there today? We've got one last hydration mechanism, or hydration reaction, and then 2 other OChem1 reactions, and 1 OChem2 reaction, NAS. So we'll pick up there on Tuesday. Then we're going to learn new reactions to make alcohols. Then we're going to review reactions that make alcohols, or reactions with alcohols. Then we're going to look at new reactions with alcohols. Then we're going to do the same with ethers, and then we're going to do the same with epoxides. Review reactions that synthesize, review reactions that use, and then look at new reactions that synthesize and new reactions that use. Thursday's class, if everything goes well here, Thursday's class is going to be a lot of multi-step synthesis application, because that's what your unit test is on at the end of next week. You're basically doing synthesis. Okay, have a good weekend, guys. I'll see you on Tuesday.